Okay, welcome everybody. Sorry for the technical delay there, but we are good to go now. So, for those who were here with us in the morning, welcome back. We've got 3 more to go. And for those that this is your first one, welcome to PDH Day. And just wanted to give you a heads up that if you want to get more content like this, go ahead and subscribe to the GSPE YouTube channel. So it's youtube.com/GSPENG, short for GSP Engineering. Beyond that, if you have any questions, please feel free to type them in the chat box and I will relay them to Ken for you. And without further ado, let me introduce Betty Jean Jordan, our Executive Director for GSPE.
Well, good afternoon, everyone. Welcome to you all. Thank you for joining us. And thank you to Ken and all of our presenters. We actually have a co-presenter today who's with us in spirit, and that is Archimedes. So I hope you read your bios that I sent you on all of our speakers. A few brief things. One, if you're not already a GSPE member, we welcome you to be one. So all you have to do is go to nspe.org, and you'll see a Join Now button in the top right-hand corner of that screen. And we encourage you to do that. Today's sessions are 1 hour each. And even though we've had a slight delay starting, we have a little buffer built in. So we should still be in good shape to stay on schedule. Remember to get your renew your PE license by December 31st. So that's just a reminder to you all. I will send out PDH Day certificates early next week. And one thing we discovered earlier today, if you are not logged into YouTube, if you don't have an account, you don't have to have one, but you won't be able to comment or ask questions directly. If you are not logged into YouTube and want to ask a question, you can just email that to me and I will post it for you. That has seemed to work pretty well the rest of the day. So without further ado, I would like to introduce our speaker for this hour, who is Ken Kagi. Am I pronouncing that right, Ken? Kagi?
Oh, that's correct, yes.
Okay. Thank you so much.
Are you still there? I lost your...
Yeah, go ahead, Ken. You're on.
Oh, okay. All right. So I was going to start out this presentation with introducing Archimedes. Archimedes is my co-presenter here. And basically, Archimedes was a mathematician, and he was born between 2087 and 2011. He is noted for his accurate approximation to pi and the square root, creating the square root. He invented a system for expressing large numbers. Back then, they didn't even have numbers. They didn't have calculators back then. But in mechanics, Archimedes discovered fundamental theorems for the center of gravity and plane of figures and solids. And he was most famous for his weight of a body immersed in a liquid, which is now the foundation for hydrostatic principles. So what's unique about Archimedes in this presentation is his techniques he used. And we're going to go over that a little bit. So when I say he did an approximation for pi, Archimedes was able to circumscribe a polygon about a circle. And he did one on the outside, and he did one on the inside, as you can see down here in this circle. And so knowing back then they knew the Pythagorean theorem, and so knowing that, he was able to actually calculate the sides of each triangle you see in there. And so the more triangles he created, the more accurate that estimation of pi was. And they known about pi for several hundred years, actually thousands of years, but they knew it was around 3 or 3.1. So this methodology he was able to increase the accuracy of actually zeroing in on the pi number. And he did it fairly accurate, in other words, to 4 decimal places. And it stood the test of time for about 150 years. So as you can see down here, this is basically his methodology used. He knew what the triangle edges were, and he was able to estimate that. And so he did it using 96-sided polygon, and his estimation was 22/7. Pi was less than 22/7 or greater than 223/71. And like I said, that was 1,500 years. That was kind of the standard of pi. So what we're going to talk about is watershed surface and channel runoff coefficient assessment. We're going to do this with a similar approach. Factors affecting stormwater runoff are surface conditions, soil type, watershed size, length of runoff, basin slope, rainfall depth. And this presentation will offer some insight into the time of concentration calculations and analogies in small watersheds for the following. I'm going to look at 4 types of surface runoff coefficients, evaluate and compare to impervious surface. We're going to use NRCS segmental equations and calculate those out and show you what those look like. And then we got 3 different time of concentration empirical equations we're going to compare to. So this is the definition of time of concentration we're going to use. This is basically the SCS method, which is probably 99% of what's actually done for hydrology out there. There are certainly other hydrographs out there besides the SCS method here. But anyway, the time of concentration, time required for water to travel from the most hydraulically remote point to the basin outlet. That's the definition that's commonly used in all hydrology studies and hydrology reports. And that's what we try to estimate. And it's probably the most difficult or the most inaccurate estimation of all in all the different hydrology parameters that are used in hydrology calculations. And I've talked to many professors saying that can have an error plus or minus 100 or 200% in your calculations are determining the peak flow. And that's really what we're trying to do here is we're trying to determine that peak flow where that hydrograph is going to max out. So first of all, we're going to look at the velocity equations using NRCS segmental methods. And for those of you who have worked in this field, I'm sure you're pretty familiar with it. But anyway, there's sheet flow or overland flow, shallow flow, and then open channel or pipe flow. So the sheet flow is basically it's a unit flow expressed in implicit channel flows. In other words, it's kind of divided down into sheet flows, but it uses Manning's kinematic wave equation to estimate this. And this is probably, not probably, but most definitely where most of the errors in calculating time of concentration for hydrology reports occur. Because if anything, especially on small watersheds, if anything meets the definition of where a tail wags the dog, this particular calculation does, because it dominates the calculations in time of concentration for the segmental method. So the equation's shown here, and it's given below, and it's actually, the kinematic wave equation is actually an iteration process, but in the TR55, they've modified it and used a 2-year storm event to calculate that time of concentration. And these are the N values that are used in that for Manning's roughness in that particular equation. And these are different N values than other Manning's equations where you use N values for channel flow. This flow is specific to like an inch or less, about an inch or 1/10 of a foot. So in the National Engineering Handbook, there's some limitations on using this equation. And this is where a lot of the discrepancy or controversy is in using this equation. McCurr in 1995 indicated that larger sheet flows, low flow lengths variables led to less accurate designs and proposed a limitation. And so they came up with this equation where it's based on N and slope. And this seems to work very well until you get into highly impervious surfaces, and then this equation starts to blow up, and we'll see that in a minute here. But anyway, I took the Manning's n values for this particular equation that are commonly used, and I related it to some impervious surfaces, actually 3 types of impervious surfaces. And so I used the average and I plotted that out and see what that looked like. Then I took those numbers and replotted them out according to even 10% impervious surfaces. And that's what it looks like. And so the next part of this velocity equation that we're going to look at is the shallow flow. And in the Engineering National Handbook, there are standard equations, and these are based on basically time over L over B. And NRCS considers the shallow flow between 1 inch and 6 inches deep. And so that's where your shallow flow comes in. And so these standard equations, as you can see, are right over here to the right. And this is a table right out of the handbook. And you could create these equations. They're very, very simple. It's just based on the depth. And so that standardizes as depth for a certain Manning's n. And so I did. I created these same velocity equations for a depth flow of 0.25 feet, about 3 inches. In other words, average in the middle, and based on the n value for that situation. So this is the actual velocity equations we'll use for comparison here. So now the last part of this segmental flow equation is the channel flow equation. And this is just Manning's equation. And most of you are familiar with it if you use it, but it's NRCS considers it 6 inch or deeper. And I took a channel flow as initial depth of 8 inches and increased it to about 16 inches over the length because it will increase as the basin gets larger. The depth will obviously increase. And so I just got a variable to there. And so these are Manning's n channel coefficients. You have a minimum, maximum, normal. And I took it and just related those Manning n equations to the flow depth for certain flow depths. So you initially have the 8 inches to start out with, and the last you have the 6 inches, 16 inches. And so these are the different velocity equations you can actually generate from those depths and those Manning n values. And you can do the same thing for channel rather than going through the Manning's equation, especially on, as you can see here, on shallow flows and on small watershed, you're going to have the shallow flows. So the same application, same velocity equations can be used on shallow flows.
Hey, Ken.
Yes.
You have a pop-up box in front of the screen, and there's off to the right, it says hide. Would you click that for us, please? There you go. Thank you.
Okay. Sorry. So these are the velocity equations that can be used with channel depth. And so now you take all 3 of these equations and you add them together, and that's how you calculate your time of concentration. And this is considered TR55 velocity or SCS method. So we're going to try to visualize what this looks like. So I took these basic information, and sheet flows, I assume basically on McKern's equation, he's saying you should be under about 100 feet to really get a good results for your sheet flow equation. So for 2 and 10%, I use 90 and 110 feet. And then for every 10%, I had a 10% drop, just to stay consistent with McKern's equation that he proposed in there. In shallow flow, I follow the same. Usually it's about 3 to 4 times the length of the sheet flow. So I'm following the same format in shallow flow here. And then what we're going to do is we're going to try to, the remaining flow is all considered channel flow. So we're going to use the channel flow calculations for the remaining length of the flow path. The equations consider flow path, geometry, slope, and surface conditions. In the National Engineering Handbook, Fulmer and Miller noted that discovered the velocity methods can underestimate time of concentration for larger watersheds. We're going to stick with the smaller watersheds, are what I call medium to small watersheds, basically anything under about 350 acres. So what this plot looks like, the time of concentration velocity looks like, we're going to take the extremes. We're going to take try to establish a boundary condition here. And we do that with the very impervious surface and the very pervious surface. And so that's what this looks like. So now we have a plot of the velocity equations. Down at the bottom, you see a very impervious slope at 12%, and then a 1% slope, you have a very pervious surface conditions. So most of your time of concentrations are going to occur between these two lines for probably 99.9% of your hydrology out there, your hydrology studies. Or your basins are going to require a time of concentration between these. So what we want to know is try to establish that blank space in between here. And basically, so the very high impervious surface basins are defined by the lower graph. And of course, the lower ones, the very high pervious surface is defined by the upper graph. And like I said, most of the hydrographs are defined by the area between. And follow interpolation for relationships of percent impervious and CN values and C values and N values will help establish these commonly used T/C values. So what I did is I took a relationship, the CN value, and this is just a common table, basically right out of the handbook of CN values. And I added them all up, and this is a standard relationship for impervious surface. And so I did an average for all your CN values. And so now we have a CN value related to percent impervious. Same with the C value. This happens to be just a Pennsylvania listing of C values, and it's based on percent slope for a basin, which is your middle. And of course, you can see they got the same relationship between impervious surfaces as you did with the CN value. So now we can relate CN values and C values together. So here's the average, what the average C value looks like here for the different soil groups. Of course, that table was listed for different soil groups. And now we have a relationship between the N value, the CN value, and the C value. And for even percent impervious surface. So what we're going to do is go ahead and plot these values for CN and C values and N values for the related percent impervious. We're going to plot these in a graph, see what they look like. So this is what they look like, time of concentration based on the percent impervious surface, or CN value, or C value. And you can see now we've filled in those two lines, the extremes. We've got some values between it. This is for a 2% slope. This is for a 5% slope. And so you can see these lines are starting to compress, and which makes sense. Your time of concentration is going to get reduced as your slope increases. And here's one for 10%. So it just compresses a little bit more, but we still have, values between those two lines. We have line we can estimate, and these are plotted time of concentration in minutes to length of flow path. And these are in hundreds of feet. So it goes up to about 6,400 feet. We're going to look at another equation, Kirpich time of concentration equation. This equation has been modeled from channelized basins. Kirpich is an accepted method in estimating time of concentration in small watershed basins. It was developed from 7 rural watersheds within the basin. And it assumes bare soil. And the slope SC is an elevation between the difference of the most remote point and the outlet divided by the flow path. The problem we have with the Kirpich equation is we got very limited factors for different surface conditions. So we have some for impervious surfaces here, asphalt. We have roadside ditches, which is one, which is just the equation itself. And then we have one for overland flow or natural grass. But what we don't have is one for wooded areas, in other words, where you have very pervious surfaces. So we're going to compare these values, these 2, 1, and 0.4, to our C values, our CN values, and our percent impervious surface. We're going to take those plots. We've got 3 plots again, and we're going to and calculate those out. We're going to take those numbers. We're going to come up with an average K value. We're going to take that average, replot that again, and come up with even percent. So now we have a fairly reasonable plot. The thing that's a little risky here is we had to extrapolate, because remember, we had no information on the wooded or pervious surfaces out there. So since we had to extrapolate out, it's a little bit risky, but not too much. You can see at 1%, the factor is about 3. And of course, we knew the impervious surface, so this end of the curve should be fairly accurate. This curve could go up or down maybe 1/10 of a point. So now we have a comparison between the CN value, the C value, and Kirpich's K values. And we can relate all of these to each other. What we're going to do is based on this value, it's all related to a percent impervious surfaces. So we're going to take these relationships and plot those out with those velocity equations. And this is what they look like. Here's a 2% slope. And you can see it crosses almost uniformly at a certain flow path. It comes down here, but they all cross pretty much uniformly. The blue is the Kirpich lines. Here's a 5%, again, uniformly crossing. Here's another one at 10%, uniformly crossing for Kirpich to velocity equations. So we made that comparison. Let's look at another time of concentration equation. This is NRCS lag equation, and this is a fairly popular equation. I'd say that's probably the second most popular I've seen in hydrology reports. Most of you see that it has it calculates a time of lag, but there's a relationship between time of concentration and the lag. It's based on surface data more so than channel flow, but you can see we've added some factors here, and this comes from our Department of Transportation, Federal Highway Administration. And a lot of people don't use those in the equation, but those should be a consideration in urban situations. This was developed by Marcus in 1961, and it was developed from heavy forest, meadows, paved areas. Again, but it was developed for less than 2,000 acres. It was developed for NRCS, which was primarily farms and fields and things like that they were developing this for. So without if you just plot the equation itself, the lag equation, and come up with a time of concentration equation without the federal highway factors in there, this is what it looks like. So you can see they get very high compared to the velocity equations that we calculated out early. This is for a 5% slope on a basin. So if we take, and this is the equation that's used, this is from the Federal Highway Administration, it's in HEC 19, these are adjustment factors for NRCS lag equation. And so that you take that equation, M and P, and you actually plot that out. I already knew what the relationship was for percent impervious compared to what the CN value was going to be. So I have a relationship, so that was pretty easy to plot out. The part that needed to be plotted out was a channel factor. And so the idea was that probably a CN 80 or above is going to have a lot of man-made channel on it. And so that's how this got plotted. And so there's a little bit of room for variation in there, but not much. So when you plot this out, here's what the 2% slope looks like between a lag impervious and channel factors, with the channel factors compared to the velocity equations. That's 2%, here's 5%. So you can see we've got some uniform crossing again of these velocity equations with the lag equation. And same with the 10%. It uniformly intersects these these velocity equations. One last one I'm going to look at here, FAA, and the reason I looked at this primarily was because it had our C value in there. That's a standard rational coefficient in there. And so I was interested in see what that looked like. This is primarily formed with basin surface data. It was developed by the Army Corps for FAA, and FAA developed this on their airports. And it's used often in a very urban situation because airports are obviously very urbanized or high impervious surface situations. So when you plot these out, FAA equations with the C values to our velocity equations, this is what they look like. And you can see the curves are almost the same, but they're much, much higher. There is no channelization factor that I'm aware of that is used in this FAA equation. But as you can see, it would take just a minor factor to bring those equations down or bring those lines down matching these. And I have played around with that, but I wish if anybody knows of a channelization factor for the FAA equation, I'd certainly love to talk to you. But the slopes are almost identical for our velocity equation. So that's, to me, that was a good indication. So what we see here is on small watersheds, time of concentration comparison graphs between the velocity equations and channelized empirical equations convey a systematic intersection for each related surface coefficient. Empirical equations provide a lower time of concentration in short flows, while the velocity equations for the same flow path exhibit a higher time of concentration. The empirical equations calculated a higher time of concentration on longer flow paths, while the velocity equations had a reduced time. The runoff time on small basins exhibit a transformation then from a surface attribute to a flow dominance to a channel attribute, flow dominance. And I call that TOC, timing outside channel, and TIC, timing inside channel. And so what we want to try to do is, how can we predict this? What we're observing here, we want to be able to predict on a regular basis in our time of concentration equations. So when I combine these equations, I'm combining Kapitch, lag, and velocity equations and comparing it to the velocity, Kapitch and lag compared to the velocity. I would cut these off, in other words, where there was excess time or the time didn't quite match down in the smaller basin. So what you see is it's time inside the channel is dominated on the other end, and time outside the channel dominated on the smaller, lower flow paths. And you can see a lot of the Kapitch and lag are almost consistent. They're right next to each other in comparison to time. And here's a 10% slope. The other one was 2%. That's what it looks like, 10%. Same thing. Lag and Kapitch run hand in hand, very close to each other. So now what we want to try to do is be able to replicate these types of curves. And so I have this equation that I came up with, just basically replicating these curves. The first one is just using impervious surface. Basically, you use percent impervious and plug that in, and then you got your square root of your slope, percent and slope of the basin, and then of course the length of the flow path itself. And I limited these to about 325 acres because these are about, if you look at that flow path, that relates very closely to 350 acres or less. 1 to 12% slope, and then 1 to 99% impervious surface. And those limitations are just based on the equations that really generated these curves to begin with. So when you plot this, what I call the UTC curve here, uniform time of concentration equation, which is in the red line, it does a very good job of simulating these other equations, where these other equations break down between surface runoff and channel runoff. This is for the 2% slope. This is for the 5% slope. Again, red lines do a pretty good job matching up there. And this one's for the 10% slope. And I did the same thing for our CN value. The other one was for percent impervious. But see, I did another equation, same idea. This one I thought was even better in accuracy in matching those types of equations. It has larger numbers in, so I think it provides that little bit of flexibility and or refinement in the equation itself. And if you remember, we based this on average CN soil relationships. In other words, that's how we were able to relate it to percent impervious surface. So if you have other CN values out there and you want to relate those CN values or other soil types, I should say, if you have other soil types out there rather than, you can see that the average CN on the red line here is very close to the B soil type. You probably wouldn't need much of an adjustment if you were using just B soil types. But if you had other soil types like the D or especially the A, then you can come in here and you can actually relate it back to a C average. This equation here will do that for you. You wouldn't have to use that graph, but you just plug in whatever soil types you're using. And so you could, if you had different soil types on your basin itself, you could actually do a combination of average CN values, just like you normally would on your hydraulic calculations. And so that's what this equation does, is it relates it back to percent impervious or average CN value.
Hey, Ken, we have a comment from somebody that you might want to respond to. So this is from Lubbock. He says, use longer TC on pre-developed sites gives a more conservative design because the allowable outflow from a pond will be smaller because the pre-developed flow is smaller because of a longer predicted TC. I believe that's predicted is what he's saying. The lower the pre-developed TC means less time with lawyers. And then he says pre-developed runoff, that is.
Okay. That's quite a comment.
Yeah, I know. I'm not sure if you were able to catch on with me reading it.
Yeah, what I'm following is a standard requirements for as the National Engineering Handbook recommends, and so I'm using those particular parameters. You want it most of the time. I find that most people don't actually go out and measure sheet flow, and if they could, sheet flow and shallow flow and channel flow, and most of them don't. It's very difficult to determine where those begin and start out there. So I'm basing it on what the handbook says as far as recommendations. For the most part, like I said, it's not actually field measured out there. So anyway, time of concentration equation, this is the one using the C value. So I developed this particular equation using the C value, and it does a fairly good job. The problem I found, though, is there's different tables across the country. The C value is not as well defined as the CN value for runoff conditions. CN value is much more scientifically developed. The C value seems to have a little more open definition at this point. I mean, there's the Ross-Miller equation that relates C value to CN values, and you could use that. Or a lot of people, like I said, a lot of areas across the country use a particular table adjusted for their area in calculations. And so that's what you see here. This one, this is an Iowa stormwater management table. The other one I showed you was Pennsylvania, but it's got the different soil types, and it's got the same. This one's based on years of occurrence. In other words, 10 years is usually kind of average or expected maximum, especially for the rational equation, because above 10 years, you got to apply a factor. And I think most of all the storms that the FAA developed on their airports from from that equation were smaller storms. And that's why you see the factors for the bigger storms, because they really didn't have a lot of data on the bigger storms, the higher or the lower percentage information. But anyway, this is an Iowa table. This one is based on the Colorado area, and it's got different soil groups in there, and the percent imperviouses, and it's based on occurrence, a 10-year or 5-year. So I plotted those out based each one. First of all, I did the Pennsylvania. I did use their 10-year storm event. In other words, the change there is in that again, in that sheet flow equation where you have the 2-year storm estimating runoff. And so I used the 10-year event rather than 2-year storm and compared it to the equations. And so this is what that looks like. And so that particular equation matches, it's very uniform and matches that break you see in the other equations between the lag equation, Kirpich equation, and velocity equation. And this one is for Iowa's. And so I used their 10-year storm, their local 10-year storm, and compared it to that particular equation. And so it seems to be standing up as I go across the country with different applications. The first one was Pennsylvania, this was Iowa. And here's one for Colorado, and it's still doing a pretty good job as far as estimating, even though the Colorado is a lot more arid type environment, and so their 10-year storm is much, much smaller. And so that's why you see the time of concentration start to increase quite a bit out there. And all these were compared for a 5% slope. So again, like the CN value equation, we have a C value equation. And of course, with this C value equation, we did an average C value, and it was based on soil types. And so if you don't have the B soil type, you can see the red is your average soil type. It relates to the B very closely. In fact, it rides right over top of it. And it's not too far off from the C type. And so the only reason you really need to adjust if you get down here in the lower C values, then you would need some adjustment. As you get up, obviously, in the impervious area, there wouldn't be much adjustment. But you could use this equation to make those adjustments to your other soil types out there and relate it to a C average, and then still use that particular time of concentration equation. So what's the relationship between Archimedes and the watershed surface runoff time? Water research for some time has shown that watersheds have a predictable response ratio for runoff times depending on the basin's physical system. And so you can see right next to me here is, right next to this is a time area diagram. And it shows the average, it basically shows the area related to time. And you can see it's somewhat linear, not quite, but it's a very linear relationship, and that's a very common response. The other in hydrological theory shows that watershed time to equilibrium, where the entire watershed contributes to the runoff as a function of the basin network, is compared to its time in concentration. The basin's runoff time, the time of concentration to its time of concentration, the basin's runoff time. In other words, if you had a very small time of equilibrium over time of concentration, it's very, very small, then the surface flow dominates. If you had an equilibrium time over time of concentration, it's closer to 1, then it's more of a channel flow in your drainage basin. And they've known that from a lot of different research. So Archimedes would exploit this basic hydrology information with the following idea. Something happened to my slide here. There it is. Okay, so he would basically, like we did in the beginning, we took those two parameters. We took a very impervious surface, which is down here at the bottom, and we took a very pervious surface. And so now we have a area that we want to define because that's where most of your hydrology occurs. So basically he did the same thing. He circumscribed circumscribed polygons around a circle and did it more and more refined till he could calculate that circle circumference and come up with a pi ratio, that 3.14 that we use today. He would employ a relationship between the time and concentration variables in basin areas. This is in the engineering handbook, and it is pretty much an acceptable relationship. This is where you start to see that linear relationship between time and area. And you can take the flows, the flow paths that I gave you on those graphs, and you can actually calculate an area out of those flow paths by reversing this particular equation. And then, of course, time of equilibrium over time of concentration. This shows up in our intersections that you start to see between the velocity equation, which is more of a channel flow, and let's say the Kirpich equation or even the lag equation. You can start to see that there's a change in the response time, the time of concentration. And so that relationship shows up basically as that time of equilibrium over time of concentration ratio. And so you try to pinpoint that and come up with an equation that can show you that change or switch. And that's what those equations did.
Hey, Ken, we got another question for you.
All right.
So Levick says, based on the last charts with higher storm events, it looks like the higher storm event is 2 years up to 100 years. It looks like TC starts to become less of the factor because the basin starts to act more and more impervious regardless of land use. So I guess he's asking, is that a correct observation or is that true?
What is he looking at? This? Does he know?
Levick, if you can let us know, is that the one you're talking about?
Any of these graphs, is that what he's referring to? So I think I understand the question, but what happens is, so this was maxed out at 10 years. Obviously, you wouldn't go up into the 100 years or 50-year storm. You would look at, normally it's a 2-year storm in calculating velocity equations. So if you add a 10-year storm, obviously it's going to increase that value slightly. And if it increases that value, then it's going to increase your time, or it's going to lower your time of concentration, actually, as you increase that storm event, because the flow depths are going to be much larger. And so that's what you see here is they start to, Pennsylvania, this is what the time of concentration shows. Let's see. This one is Colorado, time of concentration shown here. So that flow depth is going to have effect on your time of concentration. And so that depends on what depth of the storm event you actually use. And so I used it for that particular area. I hope that answers that question.
Yeah, he's saying yes. Okay. And folks, just so you know, there is a bit of a delay through YouTube. So what Ken and I are experiencing takes several seconds to get through to the rest of you. So use that little bit of delay. Okay. Thanks, Ken.
All right, so what's the correct equation? There are literally hundreds of these time and concentration equations out there. And I obviously haven't looked at all of them, but I have looked at a few of them. So the kinematic wave theory is significant in prevailing hydrology flow equations. Kinematic wave method relates flow to basin flow. Basin kinematic routing parameters define the channel shape and boundary, roughness, and slope of the flow to the routing surface. And so that's important. And so kinematic wave approximations is an accurate and efficient way of modeling stormwater runoff in both overland flow and channel flow. And this is basically a statement from Overton and Meadows in 1976. And so that seems to be the trend or the typical way we're going with some of these time of concentrations in research today. So how do these compare? If I compare those equations and compare them to kinematic flow equations to the boundary conditions out of 5 minutes. And basically, if you plot these out down here, if you change these time and concentration equations around to their surface boundary condition, which is your end value, and plot that out, this is what they look like. So the very top one is Manning's kinematic wave value, and then ASCE's kinematic wave value. In other words, that's where the 2-year storm events being used. And both of these are plotted for 5-minute time of concentration. The only difference is the depth. This was done for 4 inches. This was done with 1 inch. So you can see at 4 inches, storm event, it starts to pull away a little bit. And of course, with the 1 inch, it's much closer to the graph lines. So what do those equations look like if you want to plot it the same way? In other words, you plot it in terms of I or plot it in terms of CN or C value. This is what they particularly look like. I think the impervious surface equation does a very similar job to what the kinematic wave does, and same with the CN value. Now the C value, the C equation, when you change it around, you can see it pulls away from the graphs a little bit. But remember, we were using a 10-year storm for those particular equations. So that's the reason you start to see it starts to pull away from the edge of the graphs a little bit. So the correct equation will properly apply to the complexity of the drainage basin to accurately estimate the response time for a stormwater runoff. Time of concentration is vital to hydrograph's peak flow. It can vary peak flows by plus or minus 100%. Accuracy of time of concentrations are improved with the following understanding of the required variables that are used in time of concentration equation, understanding the limits to each variable in time of concentration equation, and understanding the basin's flow path and its flow type, length, depth, and flow. Apply acceptable surface roughness, time of concentration coefficients that correlate to equivalent hydrology surface roughness conditions. And that's where I see a lot of errors in hydrographs is they may be using a CN value or a C value for their hydrology runoff conditions, but then their end values that are using in calculating their time of concentration are not the same relationship. They're totally different end values. And so I see a lot of errors like that. So those equations kind of all automatically related to the hydrograph surface conditions that you're going to use out there. And I know we're close on time, but that's pretty much the presentation. I'm certainly willing to entertain any questions at this time.
Okay, good. We do have another one. So Lovick's obviously in the same field because he's got some good questions for you here. He says, So if you use a best fit of these curves, which equation does it most closely get to? And since you said you hadn't looked at all of them, you may not really have an answer, but I'll let you do your best with that one.
Yeah, as far as the best fit of the equations that I presented here with the CN value, the C value, what I call uniform time of concentration equation, those 3 equations, I'd say the best fit is the CN value equation. It has it did a much better job in the best fit. Again, if you're using this the C equation, uniform time of concentration, it may have a better fit depending on the area of the country you're working with, because those C values are a little bit, it depends on what area of the country you're using C values on.
Okay, any other questions? All right, let's give people just another minute or so to see if they have anything they want to ask. But in the meantime, I just wanted to say, Ken, thank you very much for doing this for us. This is always informative for everybody. I, for one, am an electrical engineer, so certainly not in my field, but it's kind of interesting to see some of the different things that go on in other parts of engineering. So I certainly appreciated it as well. Let's see if anybody else. No. Oh, and don't forget, everybody, to go ahead and subscribe to the YouTube channel. Once again, that was youtube.com/GSPENG for engineering. And the email address to send in for your PDH certificates is on the bottom of the screen right now. It looks like we did have another comment come in. Let's see. So Levick is basically, I guess, asking, so the SCS method is still the best?
Yeah, I mean, as far as those uniform time of concentration equations, that one, like I said, had the best fit, generally speaking, because I developed that based on the standards of the handbook.
Okay.
And the CN values are much better defined in SCS method than C values.
Okay. All right. And of course, lots of people saying thank you, and Steve saying very interesting presentation. So, all right. Anybody else have any questions? All right. If not, I guess we will let Ken go. Thank you very much, and you have a great weekend, Ken, and very much appreciate your time.
All right. Thank you, and I apologize for the delay there.
Oh, no problem. Thanks.
Yeah.
All right. Bye now.